Hello and welcome to part 5 of Dev Maths and Stats Refresher Course Lecture 9. And we have another example of sampling and estimators. This is based on some probability work and expected values and variances that we did in a previous lecture. So from the underlying distribution, theoretically we know that in the whole population, this is the expected value, this is the variance. But now we're thinking about the real world where all we can do is go and sample some numbers. So here we have one sample. And by looking at these numbers, can we say anything about this at all? That's what we need to try. So we see before that if that's one sample, estimator for the mean is just the mean of those. And now we can also try the estimator for the variance. Which we need an equals. The var p is the one where here we'd be dividing by 5 because there are 5 in the sample. So, as I mentioned in class, you should be able to, for 4, 5, 6 numbers like this, you should be able to calculate this by hand. Let's move that to the right place. This variance. That's the first version of the variance. The second one is var like that, just var. And when you put just var, it assumes you mean the sample variance, so it's going to divide by 4 in this case. But you should know how to calculate this one and this one for just a few numbers. And what we're going to do as before is we're going to copy this and just take loads and loads of samples, and then see, okay, on average, do these samples get as close to these values up here? And if not, how much do they vary around these? Is it biased, and so on? Just before we do that, just point out we can also experiment with these weights. Now, at the moment, this mean estimator is not calculated just by the average of these. If I type in equals average, you'll see what I mean. Perhaps it is. Yeah, so sometimes it just has to be the same there. So for example, here it's different. This one is based on just the mean of these. This is based on working out the mean using these weights. So it's 0.1 times this, 0.1 times this, and so on. So if I put 0.2, 0.2, 0.2, 0.2, let's put 1 minus that. Make it automatic. Then these will be the same because this is fifth, so this times this plus this times this is the same as the average, the same as the mean. So it's 1/5 of each one, but which is what this is doing. But previously I was using different weights because there are different ways of estimating the mean. I could estimate the mean using different weights for each observation. So because this one is giving more weight to this one, which is larger, it's coming out slightly higher than the normal mean estimator. Sometimes it will come out lower. For example, here it's giving high weights to this one and this one, which are quite low. That's why it comes out low. So we can look at the effect of putting different weights on instead of the standard 0.2s. So we'll be doing that in a moment. So for now, what we're going to do is do all this copying across. Let's just speed it up by proceeding to the next sheet. So here I've copied it across. I've got, I don't know how many, I didn't even count them, loads and loads and loads of observations. Sorry, lots and lots and lots of samples. And as before, to try and see how close we're getting to it, I've looked at the sample mean here. So that's the average of the means. That's the mean of all those means. So the mean of the sample means is very close overall, and the variance of the sample means is, don't forget, that should theoretically be given by the original variance divided by the sample size. which is 5. And so you can see it's reasonably close as well. So the variance of the sample means is given by the population variance divided by the sample size of 5. And as before, underestimates and overestimates are quite even. So it's not biased. Sometimes it's above, sometimes it's below. Not very systematic differences there. Sampling is more complicated. As before, the second has a better balance of underestimates and overestimates than the first one. So the second one is a better estimator of the population variance. However, one new thing about this spreadsheet is that we can change these weights. So if we do go for a different weighting, I'm just putting this in because it to make sure that it adds up to 1 every time. Instead of even weighting like this, if I went for 0.1, 0.1, 0.3, like this, so that's quite an uneven weighting, more weighting on the latter observations, then again the means come out sort of right compared to this. Okay, you can tell that the mean of the means still close, still reasonably balanced between the two, but look at the variance, it's got bigger. Before it was only 35. So there's more variance in these sample means, which means that when I pick one, I'm less likely to be close to this 24 because they're changing more in this line here, so it's not so good. In actual fact, what you can do mathematically is to show that this estimate of the mean is what's called blue. And you'll see this again in econometrics and so on. But it's shown, you can show that this estimator is the best linear. It's linear, this means best. Linear means it's a linear combination of the observations. It's just a fixed number times the different observations. So when you go for the one that's 0.2, 0.2, 0.2, 0.2, 0.2, which is the mean, that's blue, as in best linear. It's unbiased because you get about the same number of underestimates as overestimates, and it's efficient because that minimises the variance. The one I've got here is not very efficient because it has not got 0.2, 0.2. It's much more efficient when you have all these weights the same. Then you have an efficient operator as well as an efficient estimator as well as unbiased, and you end up with a blue estimator. So the standard average, like this, 0.2, 0.2, 0.2, 0.2, which is, in other words, in Excel, the average, that gives you the smallest variance here. And also it's unbiased, these are well balanced, and it's a linear combination of the observations, so it's blue. Okay, so those last two demonstrations should show you that this is a good estimator for the sample mean, and this one is an unbiased estimator of the sample population. So there's really one remaining problem that means that it's hard to use all this theory for practical work, and that's dealt with in the next demonstration. But for now, thanks for watching.